6.2 is addition, subtraction, and estimation. Again, we're still doing rational numbers, just like we did last time. We're talking about adding and subtracting those numbers. To start with, I want to take a look at what it means or how we go about adding and subtracting rational numbers. There's two different possibilities. The first one is that they actually have denominators that already match. So if you have fractions that have denominators that already match, in this case you see a over b plus c over b, then the denominator already has that feature in common, and we just add the numerators together. And an imagery of why that works for us, whereas what you're about to see in a moment and why it wouldn't, is that let's just say that you had a pie, and you had 4 pieces of pie. Well, if I add, let's make it 8, because it'll be more interesting. If I eat 1/4 of the, I'll say 1/4. If I have 1/4 of the pie, let's say it's 2/8, so let me say it's 2/8. If I eat 2/8 of the pie, and you eat 1/8 of the pie, well, I can add 1/8 and 2/8 because the pieces are the same size, and that makes 3/8. So that's what's going on when we add fractions that have like denominators. The problem if you have denominators that are different is that you can't add the size of those. So again, let's say that we have a piece of pie. We have not a piece of pie, a whole pie, 2 whole pies. But we cut one of them into 8ths. And we cut the other one into 6ths. Well, now if I come over here and I eat 1/8 of the piece of pie, 1/8 of the pie rather, and I come over here and I eat 1/6 of the pie, how much of the pies did I eat? Well, the pieces of pie are not the same size. So I can't rectify that situation in a very clean, easy, simple way like we just do before. Can't add the numerators and add the numbers. None of that really works. So what does work is to get a common denominator. And one way to get a common denominator is to just multiply the 2 denominators together. It's not the only way, but it's one way to do it. Right? So if I multiply the 2 denominators together, I get ED. And I can multiply these 2 items together then, A and D. So there's my AD. And I can multiply these 2 together and get BC. Again, that's not the only way to do it. It probably isn't the way to learn. But it is one of the ways that's able to be taught. So you multiply the denominator together, that's your denominator. And you multiply the 2 crosses together to get the 2 pieces of the numerator. And the numerator pieces you have it. I did put a note here because I want you to understand this may be you. Adding and subtracting is one of the most difficult things that your students will do with fractions. Usually they're really good at multiplying and dividing. Adding and subtracting is just harder. In fact, a lot of textbooks will do it in reverse order. So if you find yourself teaching in some 6th or 7th grade classroom by choice or by chance, you may see a textbook that instead of teaching addition and then multiplication, like you learn, in 2nd and 3rd grade for regular whole numbers, they'll teach multiplication before they teach addition and fractions, because multiplication and division is easy. And addition and subtraction is difficult. So our book is keeping them in this order, so we're going to keep going in this order as well. All right, so these are the 2 varieties, right? The first one, you have common denominators, which means what is 1/3 plus 5/3 before you reduce? 6/3, and then of course we will reduce. What is 6/3? 2. All right, on this one right here, 1/4 plus 5/3, they do not have a common denominator, so I need to get one, right? So I'm going to do it with the pattern that your book has established. I can take 1 times 3, and I'm going to actually write it out just so that we have this written at one point here. Plus, and then I take the other diagonal, 4 times 5. And then I divide by what we have on bottom, which is 4 times 3. And you can probably have done all of that in your head, maybe with the exception of the addition. But I want you to see that that's what's going on. So I have 1 times 3 is 3, plus 4 times 5 is 20, over 4 times 3, which is 12. And what is my grand total? 23 over 12. Unless the problem indicates that it wants it in some other form, this is fine. I.e., you don't need to change it into a mixed number. I don't need a whole number part and a fraction part. If the problem tells you to, then yeah, but this probably didn't. So we can stop right there, right? But that leads us very naturally to talking about mixed numbers because they do occur, don't they? Mixed numbers are used in everyday life to represent values that are not integers. So, for example, you hear things like, I ate 2.5 cookies. While 2.5 is actually equal to 5 halves, 5 halves would be an awkward way to say that. You wouldn't say, I ate 5 halves cookies. Right? You can say that. Go to the GC, you guys say that from the GC, and somebody can look at you funny. Say, hey, I'm serious, and we have to roll their eyes at you, right? So we don't talk that way. But the reality is that you need to know, and your students, if they're as they're working with fractions, need to know that those are equivalent. Because while it's more natural within context to talk about 2.5, 5 halves is lots easier to work a math problem with. Working a math problem with 2.5 is much more messy than it is to work a problem with the improper fraction version of it. So we need both of those. So we need to be able to change between them, in other words, okay? So here's an example. We have the improper fraction, 14/3. We want to put it into a mixed number form. So when you have this situation, this right here is all about division. You interpret that division sign between the 14 and 3 as division. And you write it as a division problem, which means you write 3 on the outside of a division bar and 14 on the inside, and you actually physically divide. So how many times will 3 go into 14? 4 times. And I say, what is 4 times 3? 12. And I say, what is the remainder? 2. And when you're first learning division at about 3rd, 4th grade, you write this as 4R2. Remember that? But once you're actually working with fractions, you cease doing that. And this is about 5th, 6th grade. And you don't write it as 4R2. You write it as 4 2/3. Right? It's 2 out of the original 3. So this would be the mixed number representation for 14/3. Now, when you turn something from a mixed number back into an improper fraction, it's about multiplication, addition actually. So we multiply and add. And we're going to do this, I'm going to make it a little bit bigger. The negative is part of the answer, but it's part of the answer, it's just a negative number. So I'm going to ignore the negative for the moment, okay? My answer is going to be negative, but the work in between this is needed. So I'm going to write down 3 5/8. And if you remember, what you do is you multiply here. 8 times 3 is 24, and then you keep going around and you add. 24 plus 5 is, what was it? 29. And you write that result over the original 8. Make sense? Do you guys remember this? Good, then it will be reviewed for sure when you get there. All right. There are a couple properties that you've seen, and you've seen them, if you've taken Math 1, you've seen them expressed explicitly in Math 1. The inverse property and the addition property of equality. If you haven't taken Math 1, that's okay. You've seen them used before, whether you've seen them described this way or not. So the first property talks about inverses and rational numbers. So if you have any number a over b, there exists a unique rational number, negative a over b, and it has the property that when you add those two numbers together, a over b and negative over b, a over b, you get back to 0, right? So you get 1/3 and you got negative 1/3. You got 14/8 and you got negative 14/8. And they all have that property, okay? Well, at least nearly so. Well, actually, they all have that property. There's one that's nearly so, and I'll get there. All right, 6/9 is an addition property of equality. And what 6/9 is saying is that you're able to add a value as long as you add it to both sides of an equation. Did you guys do that? You could do that in algebra, right? You're allowed to move things between sides of an equation using addition. I can add 5 to both sides of the equation, it doesn't change anything. It's like taking a scale. If I take a scale and I add 5 pounds on the side of the scale, and I had 5 pounds on the side of the scale, and it was balanced to begin with, it would be balanced after I put 5 pounds on both sides. And that's all this is saying, okay? These are properties we use extensively when we do algebra, right? So when your kids, your students hit middle school and they start working with algebra, they use this stuff all the time. So I want to show you how prevalently you use it by doing an example. You know what? I think we're going to stop this. No, we go till 3:15. We're good. Tell me what. Tuesday, Thursday, just throw me for okay. All right, so I'm going to show you how this works when we are actually working a problem. So our goal in this problem is to solve for x, right? Yeah. So one of the things we need to do is we need to get that 2 1/2 away from the x. And how do you do that? By adding. So what do you add? 2 1/2. Why is it that you want to add 2 1/2? Yes. Yes, it does. Now, so we've used the word cancel several times today already. Did you know that the word cancel is really confusing to students? The reason it's confusing to students is because we say it for so many different things. So when you guys just said the word cancel, you mean it adds to 0, right? And so when Audrey said cancel on the last section, she meant it just went away, right? And sometimes when we say cancel, we mean it cancels to the number 1. So we want to be really careful with the word cancel to be a little bit more explicit with what we're meaning, because it has so many different meanings. So what you're saying on this one is that we want it to cancel a 0. In other words, we want it to add to 0. So that's what we're going to say, okay? So we have chosen to add the number 2 1/2. And in doing so, we chose that number because it's the additive inverse, right? I think we call that theorem 6-8. So the directions say to solve for x in this problem, and I want to show you why each of these steps is allowed. So this right here is allowed by theorems 6-8 and 6-9 actually. 6-9 allows us to put the number on the same side. You know, you can add the number, subtract the number to both sides of the equation. We chose this number specifically because theorem 6-8 says there is an inverse that we can choose, and when it does, it adds something to 0. So we're using both those properties. All right, so now I have x equals, I have 3 1/3 plus 2 1/2, and I want it to submit to you that there are 2 ways to do this problem. And you probably learned one of them and not both of them. And I suspect you learned the same one that I did, although I could be incorrect. So I'm going to show you both ways to do the problem. I really don't care which one you use. You can use whichever one you like. But please allow yourself the possibility that the one that you've used before, you may not like as much when you see the other option. Okay? So please approach this with an open mind, and let's take a look at the 2 methods. I'm going to do the method that I don't think as many of you know, and that's the method of mixed numbers. Okay? So method 1. And these don't really have names, but I'm going to call it mixed numbers. Method 1 actually keeps these numbers as they are. I have 3 1/3. Let me say it this way, actually. I have 3 plus, okay, 1/3, and I have 2 plus 1/2. That's what 3 1/3 means, right? I have 3 of something and 1/3 more. I have 2 of something and 1/2 more. And in the mixed numbers approach, I add the whole numbers together. 3 plus 2, and I have 5. And then I have the 1/3 plus the 1/2. Now I'm going to add those fractions together using the same method that we did earlier, right? Or a variety other version of it you've seen is fine. So I'm going to multiply this diagonal, that's 2, plus multiply this diagonal, that's 3. And I'm going to divide by the 2 denominators multiplied, that's 6. So I have 5. And then what is this fraction? Not yet. It's not 1. It's 5/6, right? Because we're adding the numerators together, not multiplying. So this is 5 and 5/6. Well, let me show you another way of doing that, which is probably what you're thinking of. You can tell me if I'm wrong. But another way of thinking about this, aside from this sort of diagram approach, which is what your book is using, is to think about it like this. Here's 1/3 and 1/2. And you do this 2 times 2. And you do this one 3 times 3. Yeah, it's the same thing. It's just not quite as visual. This is really, a lot of your students are going to be visual learners, and this one's really nice in terms of a visual pattern that you can follow. This is fine. It works okay as well. Your book is geared towards this, but it's fine either way. Okay. Yeah, so of course I still get 2 plus 3 over 6, which is 5/6. Okay, so this is the mixed numbers approach, and my guess is that's probably, if you've not seen both of these, that's the one you've probably not seen. This other one is probably the one that you have. So here's method 2. This is the improper fraction approach. So what we can do is that we can take the 3 and the 1/3. Whoops. And the 2 and 1/2, and we can turn them into mixed, right, to improper fractions, right? So we did that on the previous slide, so we'll make quick work of that. I have 3 times 3, which is plus 1 is, this is 10/3. And then I have 2 times 2, which is 4, plus 1, which is 5, so I have 5 halves. And then I can do the same process, either the visual sort of look of what I've been doing, or what Audrey is suggesting up here, where we just write it a little bit differently. That's fine too. And we get the same denominator. So I'm going to keep going with what your book does, just because it's very nice and visual, and if you haven't given it a try, it's good to see it several times. So I have 10 times 2, which is 20, plus 5 times 3, which is 15, over 6. And if I add them together, then what do I get? Oops. This is 35 over 6. But if the problem started out with mixed numbers, the problem has to end with mixed numbers, which means I have to turn this back into a mixed number. And that's where I didn't have to do that over here, right? That's kind of nice. So if I turn this back into a mixed number, I divide. How many times will 6 go into 35? 5 times. 5 times 6 is 30, the remainder of 5. So this becomes 5 and 5/6. Now, the only method I ever learned was improper fractions. It's about the method I learned. I'm a big fan of the other method though, because it keeps your fractions smaller, it's a lot easier to work with, less error in terms of multiplying and whatnot. And I'm a fan of the fact that I don't have to turn it back into a mixed number at the end. So, like I said, I don't really care which one you use. So it's perfectly fine if you're just absolutely in love with the second method, because that's what you've learned all the way along. You can use that, but be aware that the textbook that you have might give you an alternate option at some point. Okay. All right. Definition of subtraction, and it may look a little bit weird. Subtraction is defined in terms of addition. And that's actually a lot of times how subtraction is taught with whole numbers as well. We do something like this with a child. We say, we want them to learn what 5 minus 2 is. And the way we do that is we say, well, what do we add to 2 to get back 5? Right? And they have to think, what plus 2 is 5, and they say 3. And that's subtraction. Okay? It doesn't look like subtraction because the equation that they have on this page they brought home or whatever says 2, and it's a blank spot. We've got addition in there. 5 on the other side, and then fill in the blank. So this is one of the ways that we start talking about subtraction even with whole numbers. But it works and is definitely true for rational numbers as well. If you have 2 rational numbers, A over B and C over D, and we want to talk about subtracting them, then the question is really, what do we have to add back to C over D to get back A over B? And it's some other rational number. In this case, I'm calling it E over F. And if you take a look at this other theorem, it's a theorem that you, of course, know. And in fact, I have this distinct memory from 7th grade, somebody telling me there's no such thing as subtraction. I don't know if you guys ever had teachers that did that too. You're just like, what are they talking about? There's no such thing as subtraction. Because it's not subtraction, we have two names for it. It's not that there's no such thing as subtraction, but it is adding a negative, right? So we can express A over B minus C over D as A over B plus N negative C over D. And that's what this there is saying. So let's actually take a look at, I've got one more slide of some descriptions. Subtraction, the description of it, which is addition, right? You have the like denominators, you just subtract the numerators. And if your denominators are not alike, then you have to get them to be alike. Either using the same method we did before where we cross them out, you would cross multiply them and we multiply the denominators together, or by multiplying the denominators together and seeing a little bit different visually. Either way, that will get us the different denominators to become like denominators able to be added. So I'd like for us to take a look at a great example, and so it's a great example because it has so much in it. So we're going to take a look at the problem. We've got Martine, and she buys 8 3/4 yards of fabric. She wants to make a skirt using 1 7/8 yards, pants using 2 3/8 yards, and a vest using 1 2/3 yards. How much fabric will be left over? So you can do this problem in a variety of ways, right? One option is that you could actually take the 8 3/4 and subtract 1 7/8, and then subtract 2 3/8, and then subtract 1 2/3. And visually, if you imagine her doing this, that's what she would really do, right? She'd roll out the fabric on the floor. If you've ever done any kind of sewing project, whatever, this is what you do. You roll out the fabric on the floor, and you put the patterns on top of the fabric, and you cut them out one at a time. So literally, that's what you would do. You would cut off each of those pieces one at a time, right? But our question actually asks us for the end. What little piece of fabric is she left with at the end? So an alternate way of doing this would be what? You could. And not that it changes, the difficulty of the problem, but it is another way of thinking about the problem, right? You can add the 3 pieces together that she wants to create and then subtract that from the original 8 3/4. So I'm going to suggest that let's do that one because I think the math is maybe just a little bit cleaner for doing it because I only have to subtract once instead of 3 times. So let's give that a go. So we're going to take, and literally what we're saying we're going to do is we're going to do 8 3/4, and we're going to subtract a sum. The sum is 1 7/8 plus 2 3/8 plus 1 2/3. Okay. Now, since it is less familiar to you, I am going to do that method 1 from last time on this problem because I want you to feel how that actually works again if you've never seen it before today. So we're going to take the numbers inside parentheses and we're going to add them together. The way that we add them together is that we add the whole number parts first. So I have 1, 2, 3, and 4. That's the whole number parts, right? And then I have 7/8 and 3/8 and 2/3. And a couple of those can be added together right after that as well. Can't they? Sure. So I have 4, and then I have 7, 8, 9, 10 eighths. Again, we're faced with a couple of choices. What could we do with 10 eighths? There's 2 different things we could do right now. We could reduce it. What else could we do? We could add it to 10 to the 2/3. That's a possibility. I guess there's 3 choices I thought of it. That's where we could. Right. Yeah, we could turn the 10 eighths into a mixed number, right? So I think at least reducing the 10 eighths is helpful. So let's do that because it makes the fractions denominator smaller, and we're going to be working with denominators. So let's do that part at least. So what do I get with the 10 eighths if I reduce it? 5/4. And I think Sarah's right. It does kind of just add an extra step if I decide that I want to take 5/4 and turn it into 1 1/4. So let's just leave it at 5/4 for now. But recognize that if you wanted to turn it into 1 1/4, it'd be okay for everything. All right, so I need to add 5/4 and 2/3. So let's do that. And we'll do that by multiplying 5 times 3. So I've got 15 plus 4 times 2, which is 8, over 12. Okie dokie. 15 plus 8 is 23. I feel like I've written 23 over 12 on the board once before today. I think I did. All right, so 23/12, how can that be reduced? Not reduced, I shouldn't say that. How could we change it to an extent of this? It's more than 1, right? What would it be? 1 and 11/12. It will be. And you can write out the division step for yourself to see that if you need it. I'm actually going to do this and come on back up here so that I'm not extending my screen any further. But I've got 8 3/4. I've got minus 4 plus 1 and 11/12, which looks suspiciously like 5 and 11/12. Doesn't it? Here's the thing. Subtraction with mixed numbers has a little bit of a nuance with it than the addition didn't. I can subtract the whole number parts and I can subtract the fractional parts. But let me show you what's going to happen. So I can do 8 minus 5. 8 minus 5 is 3, right? Plus 3/4 minus 11/12. Well, I literally can't take 11/12 away from 3/4 because it's not big enough. I can, however, do the crosses and everything just like I did before. So I'm going to do that, and we'll see what happens from there. So I've got, you know what, in fact, I think I'm not. This one actually has a smaller common denominator than it would if I did my crosses. What is the least common denominator between 4 and 12? 4 is a factor that it has. 12 will be the least common denominator. In other words, I can turn my 4 into 12. What would I need to multiply 4 by? 3. And then I actually have a common denominator of 12. So let's actually do it that way. If I do this, I have 9 minus 11 on top. I have 12 on bottom. Here's this 3 plus business out in front. So what's 9 minus 11? -2. So right now I've got 3 minus 2 over 12. Right, addition is the same as the multiplying negative. This is subtraction negative. 2 12 can reduce. Pounds 1/6. Very good. So this is 3 minus 1/6. So if I have 3 of something and I subtract off 1/6, what will I get? 2 and 5/6. There's a couple ways to do that. If you can do that in your head, that's fabulous. If you have difficulty sort of imagining that, what you can do is you can take one of these 3 and you can borrow. You can turn that 3 into a 2 and turn the one that you took away into 6 over 6. The 6 over 6 is the number 1. You do 6 minus 1 is 5. It's borrowing just like you borrow when you do regular subtraction from numbers. Okay. 2 and 5/6 what? Yards. After all that work. Go back up to the problem to remember we're talking about yards and that work. So, is this a long in-depth problem? Yeah. That's why I said it was a nice one. It gives you a chance to see a lot of the different methods that are all rolled into one place. All right. Yes?
How many of these skills do you want us to have?
You don't have to have all of them. Because I don't know your math abilities, I tend to show more on the work, on the building you have to have. You should have several of them though. I mean, you're really not going to be able to jump from here to here. And one of the things that can use a calculator, but I want you to be thinking from the perspective of an elementary, early grade school or middle school student. When they use a calculator to do all these things, probably not. So try to keep that in mind as you're working, that some of your steps need to show what you would be thinking or doing if you were doing this math with them. Does that make sense? All right. You know what? We have 2 slides left, and I think that it would be good if we just hold off on those last 2 slides till next time, okay? So we'll finish this next time. Give me just a sec.